So we've seen that the total delta F due to a change, due to a displacement h in the direction of our u vector is approximately equal to fx h ux plus fy h uy, rate of change in the x direction times the displacement in the x direction plus rate of change in the y direction times the displacement in y direction. We ask now, what's the rate of change of F with respect to displacement in the direction u? This isn't quite an accurate statement. We should probably call this the average rate of change of F with respect to h, and not using h quite correctly here. There are some technicalities in this, but you should get the idea. The average rate of change of F with respect to displacement in the direction of the vector u, now where that displacement is represented by h, is delta F over h. Change in the value of F divided by the distance we've moved in the direction of the vector u. So we ask the question, what is the change of F per unit of displacement h in the direction u? Well, delta F, as we've seen, is fx times hux, rate of change in the of F with respect to displacement in the x direction times displacement in the x direction, and the same for the y direction. So that delta F over h, which is the change in F per unit of displacement in the direction of u, change in F divided by the displacement, is the change in F per unit of displacement. Simply dividing through this expression by h, we see that that's fx ux plus fy uy. We can make perfect sense of this expression, rate of change of x, rate of change of F with respect to displacement in the x direction times the displacement in the x direction. Rate of change of F with respect to displacement in the y direction multiplied by the displacement in the y direction. Now, in the limit, as h approaches 0, the error of our approximation disappears. That is, the smaller h gets, the less fx and fy can vary within the region. And we call that limiting value of delta F over h, we call this limiting value the directional derivative of F with respect to direction u. And we could write that. I have a little room here. Let's write that out. Now, d sub u is what we're going to call the directional derivative of F of xy, is the limit as h approaches 0 of our delta F over F. Now, we haven't algebraically written out these expressions, so what we're doing here isn't completely rigorous, but we understand that in the limit as h approaches 0, the approximation of these two expressions, and I really should have written that with approximately equal signs, the approximation becomes exact. The approximation approaches the limit of the exact rate of change of F with respect to motion in the y direction. So the notation is d sub u of f of xy, the derivative with respect to direction u of f of x sub y, and for any function f of x sub y, that directional derivative is just fx times ux plus fy times uy, where fx and fy are evaluated at the same point as f of xy. Again, we call this the directional derivative of the function f in the direction u.